will actually be a lot more from the fire water storage tank. And then, again, let's keep assuming that the power has still not been restored to the site. What then do you do? Again, simple refill actions. There are pre-planned hookups that are provided outside the reactor building. Any water source, external water source that we might have, whether it's a lake or a pond or a river or even the sea, connect the hose from that source to the outside connection that already provided with a very commercially available 12 horsepower driven pump to be able to pump water and replenish the ICS and PCCS pools. And again, you're not dumping that water into the reactor pressure vessel. You're keeping your investment intact. What is happening is the seawater or the other suboptimal quality water is just going into ICS pools. And the heat exchangers have been qualified to work with that kind of water as well, because the heat transfer coefficients and the materials used in the heat exchanger are designed to work with suboptimal quality water as well. So really, at the end of it, you're looking at an almost, a very long indefinite source once you have a large body of water available and a 12 horsepower diesel pump available to be able to pump water from that source into the reactor system, the ICS, PCCS pools to cool the reactor. Obviously, at the end of 11 days or 12 days, the heat is already at a very low level, so you're already fine with that. So really, what we have here is a case of, if you don't want to credit any operator action, any remedy reaction, whether it's connecting putting on the diesel to the pump of the fire water storage or making external connections, then what ESBW allows you is 7+ days of hands-free operation without any DC power requirement. Obviously, in the case of a prolonged station blackout, which is when you would not have any power supply at all. So just what I described in terms of simple refill actions, let me show a little video here to make it more graphically.
At any time, the operators can take simple actions to refill the heat exchanger pools. Outside the reactor building, a permanent diesel pump is located in the fire water storage building. The operator can start this diesel pump to transfer water through dedicated piping from the large water tanks to the heat exchanger pools. Large diesel tanks provide a secure supply of fuel, with a rugged building enclosure providing protection for both the pump and tank. The simple operation of the diesel pump within about 8 days of the loss of power event would ensure continued operation of the isolation condensers and core cooling. If in the unlikely event the rugged diesel pump is not available, dedicated refill lines are available outside the reactor building to provide a simple but reliable means of refill. Many types of pumps can provide sufficient water for refill of the pools. Backup pump operations could include a fire truck, small hand-carried pump, or even a local farmer's tractor-powered irrigation pump. This breadth of options is the result of the pools not being under pressure and open to the atmosphere. A small hand-carried pump could be easily stored securely on site, or, if needed, could easily be transported in a small pickup truck or van. Simple hookup of the pump to pipe connections outside the reactor building would be needed to draw water from a portable water truck or a small body of water nearby. Once the pump is in place and connected to a water source, refill of the heat exchanger pools can begin. If fresh water is not available, salt or brackish water can be substituted with no negative impacts to reactor cooling.
So that's really what we mean by intelligently using fencing net in addition to redundancy and diversity to be able to address situations that we are confronted with these days, what you might categorize as anticipated unknowns. How do we plan for that, and how do we address those should those events arise? Let me just quickly touch a little bit on additional advanced safety features of the ESBWR. As I mentioned earlier, the nuclear industry, the learning industry, has learned from a lot of events in its history as well as in its outside of the industry itself, which is 9/11. So just like other advanced reactor designs, ESBWR is qualified to survive aircraft impact. As far as hydrogen mitigation is concerned, the very first place, hydrogen generation is preempted in the ESBWR because the worst case design basis accident, the operation ensures that water will always be covered on top of the active fuel by at least a meter high. So there will always be water 1 meter above the top of active preempting hydrogen generation. However, as a defensive depth measure again, the containment ESBWR is naturally inert and the HARS or passive water catalytic requirements are provided for hydrogen removal, as well as a high pressure rated vent pathway for containment with airspace. There's also the core catcher or the BIMAC, as we refer to it, the baseman, melt arrest coolability device, which is located within the primary containment and precisely with the objective of containing the chloria should it make its way through the RDV and minimizing the core concrete interactions, so preventing a severe accident. So having talked about all this regarding the safety aspects, let me just take a little bit of time on the ESBWR design itself. As I mentioned earlier, challenge is really how to simplify the design, make it safer, how to rethink defense in depth. But all of this we want to do in an innovative way, yet take the design evolution, because nuclear industry for one is not light and it's not long radical innovation or radical use of faith between one generation of technology to the next. And ESBWR is no different because it is an evolutionary design. It uses natural circulation. It's not the first time the reactor design has used natural circulation. Reactor designs in Netherlands, in Indo-U.S, in California, Humboldt Bay, which have since been shut down but have operated for 13 and 30 years, have used natural circulation and have been primary sources for us to qualify natural circulation in the ESBWR. It's a large source of baseload power, generates 4,500 megawatt thermals, which translates to about 1,594 megawatt electric, depending on site conditions, which could change depending on water temperature that's used in the reactor systems. And again, going back to the theme of evolutionary, I mean, the ESBWR program has its roots back in the 80s when the ESBWR program started. A lot of the testing that was done, eventual scale up, even during the certification process, has been extensively utilized for certification and development of the design basis of the ESBWR. And it really goes back 30 years, and sources of data that we use come from real-world operational data as well as additional confirmatory tests and stuff like that. One of the other clear advantages is compliance with the latest NRC regulations. Having the FDA and the FCR since March 2011 about to be design certified with the status of the certified technology. And so, talking again about lessons learned, it gives us the benefit of having at its disposal the universe of all the lessons learned of pilot manager or ESBWR has been certified. So that's the other advantage as well as for the ESBWR and other task designs. Again, just to reiterate the point, every component, most of the components that are used in the ESBWR technology have been used previously. They're standard on the BWR designs, and they have been used previously, although in a different scale or a different level of output. But they have been used in operating history, testing and analysis has been extensively conducted. And this is just a table that shows you some of the components that appear in the ESBWR. The isolation condenser that we talked about is really not a new feature also. Indo-U.S used it, Tarapur has it, Dresden, 1, 2, 3, all the plants in the U.S. that are listed over here have had isolation condenser as part of the design. We just extended the purpose and the scale of the isolation condenser we use. It has further been tested specifically for the ESBWR in the Panthers test program. Natural circulation I mentioned already, Indo-U.S and Humboldt Bay, as well as a bunch of other components and systems that have been utilized in the ESBWR. So the point I'm trying to make here is it's not first of a kind. It is a scale design and it's rooted, it's design based, it's rooted in real-world operational data and tests. And these are some pictures of the actual tests that have been conducted. All of this body of data that I talked about going back 30 years was subjected to rigorous scrutiny as part of the NRC review process and independently verified. And as part of that process, again, we had to go through the additional confirmatory tests, and we have some of these pictures. The PCCS, you have the giraffe test, the test in thermal hydraulics, the GDCS, integral system test in Italy, and the BBB tests and so on. We can't lose sight, even in all this talk of safety. Safety is primary, most important. We can't lose sight of cost as well, because in the end, it's what is going to make the technology feasible. It's what the utilities are, the ratepayers, city they purchased. So the ESBWR has also been designed with that aspect in mind. Again, the simplified design helps the ESBWR with that objective. First of all, there are no recirculation pumps. It operates on natural circulation. And as soon as there are no recirculation pumps to cause force convection, which is not necessary in the ESBWR, you also get rid of all the associated motors and valves and electrical cables or control systems and associated with maintaining those active systems. The ESBWR is a boiling water reactor design, so it's a direct cycle boiling water reactor. Does not require steam generators like PWR designs. So it does away with, some of the folks that we have talked to are totally surprised to not see a steam generator in the ESBWR because of their lack of reality technology. But there are no steam generators in the ESBWR, and typically these steam generators are 230 in equipment, as you're all pretty much aware, and the replacement schedule is mandated. The Advanced Digital INC is on the fact of the ESBWR. It's the only digital INC architecture. ESBWR's DCIS is the architecture that has been fully approved by the NRC with no issues. And again, it supports safety-related digital INC, supports the 72-hour hands-free operation, and also simplifies operator response to situations. It's based on human factors engineering and so on. That's a whole different topic from a separate presentation to address. ESBWR is designed for a 60-year service life. It's a requirement. All the capital-intensive components of the design, such as the RPB, the steam turbine generator motors and casings, the electrical cables, the suppression wheel, all the capital-intensive components are required to be designed for 60 years. And that includes the maintenance and the refurbishment program that will have to go along to assure that the 60-year design life has been achieved. And that is really important in a sense because that's where the true economic benefit of nuclear power comes through is once the capital asset is appreciated, you are really producing electricity based on power at very low production costs. So either you use that 60-year period to extend your depreciation schedule, or you use, if you want to keep the same depreciation schedule as you do now, then you have a high rate of internal return on the 60-year period of time. And so, in the end, we believe ESBWR is one of those advanced technologies that holistically addresses the issue of plant safety, of continuously enhancing plant safety, especially in response to the situation that the challenge that we have in front of us. It's a Gen 3 plus evolutionary design. So, in closing, really, just like the 3 Mile Island incident of accident interaction, it's more than an incident, and Chernobyl, and the events that happened in Fukushima will remain within the nuclear industry and shape the thinking of the industry for a very long time. But however, even as we learn more and more from that event, a few nuggets of design wisdom is already kind of coming before, which is what, if you would hear from Dr. Banerjee's keynote address yesterday, he addressed those, which namely, emergency core cooling systems being passive versus active, the advantages of being passive versus active. Less is more when it comes to reliance on external AC power for safe removal of nuclear, or more the better when it comes to time between loss of AC power and onset of core damage, or designing pre-plant hookups, or thinking ahead and designing that into the plan to be able to replenish good water inventory should the need arise. So all of those things are being crystallized right now, but ESBWR is already incorporated these features into its design. Not as an afterthought, it's really been done as a forethought. And, so we really think the ESBWR is, in today's time, the challenges ahead of us, passive safety design, and technology for customer technology. And with it being modern and advanced and soon to be just certified, its design base is built on universal lessons learned from experience over past decades. So, with that, I'd like to thank you for your time.